Estava falando de você outro dia, agora.
Porque você está indo para Xangai.
É, eu fui para Xangai. Mas aí veio um monte de coisa. Não, não, mas eu falo aí. Lá no Rio. Eu vou voltar agora para ir para festa. Então, nós fizemos um montão de chineses.
Eu sei.
É um pessoal bacana.
Não, é um pouco do UCC, eu acho que tem ele para fazer o roteiro.
É. E eles fizeram lá, até. Aí um deles chamava técnico. Eu conheço isso ainda. É tipo isso.
Então, hoje não vamos ter dia de debate com você, está fazendo nossa, Carol, está tendo a curadoria. Ele está, por isso que eu estou aqui várias semanas.
Eu também vou fazer alguma coisa no vídeo. Mais tarde. Eu vou fazer uma na galeria da frente.
Sim,
É. Ah, que legal.
você vai voltar para o
Eu lixei um nervo. Ontem eu não conseguia botar o pé no chão. Ontem era melhor. Estava com a porta. Mas aquilo é muito feio. Eu não consegui pegar um avião para aquilo de manhã, não. Eu vou devagarzinho. Hoje não, vou. Depois daqui eu já vou e pego o avião e volto. Volto. Vou jantar. Volto a Bienal, mas assim, eu vou e volto. Eu não estou podendo isso.
dia 6 de
Qual Marcelo? Não?
é o dia 7
Fiz um negócio com ele lá em Vancouver agora.
Ah, é, pois é.
Mas legal que você vê. Oi? Tá bom. Tá bom. Alô, alô. Alô, alô. Olha, pessoal, é só para avisar que a apresentação vai ser feita em inglês, mas nós temos, quem precisar de tradução, tem os foninhos estão na sala ali atrás. E se por acaso alguém não conseguir sentar, vai ter um streaming numa televisão também na sala de trás. Vai esperar mais um pouquinho, só para ver se... Tá bom. Mais 2 minutinhos. Tá bom, né? Tá muito escuro? Mas eu tô feio, eu não dormi direito, tá bom. Tô com cara de bactéria. I think no, when we start the projection, maybe we just turn it off because it's kind of it's hard to see it. Yeah. Yeah. More people coming. Oh, let's turn around. Yeah, my dear. Yeah, yeah. I have to meet them because I have another project that I want to talk to him about. Because I'm doing a train station in London, maybe doing so. I'm shortlisted for only two artists, and I want to use lenticular printing. So when the train comes, you see kind of like three. There's like two stage flats, 100 meters long. Like the basis. See if we can come up with something about it. Shall we? Okay. All right. Ah, yeah. Perfect. Oh, okay. Okay. And after, after we can just isolate. Okay. Good morning, everybody. I'm extra surprised by the generous turnaround. I mean, for because myself, I don't see myself waking up on Saturday morning, especially in a nice day after so many rainy days, to come to see an artist talk and a scientist talk together. So I'm very flattered by your interest in this conversation, which is it's a rather unusual one. When people talk about art and science, it seems like you're talking about two entirely different worlds, and it's there is a historic of uh, possible collaborations between artists and science. I'll name a few, but I'd like to start about uh, giving a little background on why we came to be sitting here, me and Tal, talking to you about a certain convergence in what we do. The Nobel Prize winner Richard Feynman, in his autobiography, Are You Joking, Mr. Feynman? He mentions one collaboration he attempted to do with the installation artist from California, Robert Irvin. Robert Irvin is perhaps an artist that relies a lot on optical information. He's as scientific as it gets when you're talking about an artist. And according to Feynman, they spent, I think it was a month together in a project promoted by Caltech to put artists and scientists together. Well, the conclusion, when he gets to his final remarks, Feynman says that it felt it wasn't very productive. But if there was one thing that remained, is the fact that he felt that they were pointing at the same things, but describing it in different languages. I go a little bit farther to that, because I think when not because you're here, but I love scientists, I love science. I think because I'm always feeling that when you're dealing with science, you're dealing with the other side of things. I simplified a little bit the workings, the engineering of the world that I perceive, that I live, from the time I wake up to the time I go to bed, and it's very simple. That's just, there is a world that happens in your mind, and there's a world that happens outside your mind in the material world. And when you think about the importance of really tapping or feeling what's beyond your whenever there's simultaneous translation, I get a little bit, it's like the sandwich ishi woman, like but what's beyond the immediacy of your senses. It's a very important thing, because artists were always turned towards nature, towards what was there, and trying to represent that, trying to make this internal. But why I have a hard time like dividing education and culture. For me, I tend to make very broad generalizations and be very holistic about everything. But then, if you go a little bit back, when was that? Then science sort of separates from art. Before it wasn't like that. If you can think of in terms of like, there's a lot of that information that is pertinent to art and science that we use today, that was integrated. There was at one time scientists and artists were pretty much the same person. In primitive times, this is like what the figure of the shaman. He's a sort of an artist and scientist because he holds power on both ends. Alchemists, which probably define both of our trades. They were artistic scientists and they're scientific artists in a sense. Not that the information, everything that they developed, was true or held water scientifically, but they had really beautifully imaginative ways to describe it. I have a friend who's an astrophysicist. His name is Lee Smalley. And once I could not help, but he was telling me about calculus that he's doing about objects that manifest themselves in over 10 dimensions. It is impossible for an artist to imagine that, because that only occurs in a linguistic symbolic level. He can actually see, or he perceives these objects because he's totally into the mindset of it. I couldn't possibly think, because I was trying to give it a form. It's very hard, when you try to jump to the other side. But it became an obsession to me over the years, how to actually make these things come back. And I realized that I wasn't alone in this project. At one point in history, for science to develop, it had to split, to divorce itself from art, from the idea of interpretation or the interpretation or sentiments or mind. To give you an example, at the beginning of what we call the scientific process, you have Galileo putting two spheres on a ramp and letting them go simultaneously. And according to the way these spheres behave going down this ramp, he would conclude that this is a physical law. But for that to happen, there's got to be an observer. There's got to be an observer. There's going to be somebody looking at this. If these spheres, they go down a ramp and they behave in a specific way, well, what if the person who's looking at them is autistic, is distracted, is schizophrenic, is blind, So by saying that there's some kind of God-like eye that's behaving, that it will say that this is it. And if it behaves that in a number of ways, every time you throw the spheres, they will go the same way independently of who is looking at them. That constitutes a physical law. And that's something it creates a standard that you can build on. And this way was great because you could ignore the presence of mind entirely in the construct of a physical, of a scientific process. And that enabled the scientific process to advance and also enabled the artistic process from advance. Because without physics, you could have angels, chubby angels with little wings, they could fly. If you apply gravity to those paintings that you see in 18th, 17th century, 16th century paintings all over Europe, the cherubs, the cupids, the angels will always be like on the floor with bruises and their broken arms. The angels cannot fly. I think it's gonna be a time. I think it comes down to a point where there is a need for these two, for mind and phenomena, to converge again, so we can make a science that's truly whole. I sense it in the cognitive neurosciences, for instance. It's interesting that it took us. We had to be in the middle of the 20th century to come up with the conclusion that experience alters phenomenon. That the fact that you're looking at something, you change it. Artists seem to know that all along. And probably scientists did, but they didn't want to admit that. But the fact that when I'm talking to Lee Smalling again, he says that he was trying to figure out what happens if two black holes would collide. Ultimately, he would have to explain this to somebody like me. And even people like Lee Smalling, who can only relate his findings to half a dozen people around the world, you have to write a popular book, and something that people would understand, some people could digest, at least to make it easier for people to make his findings relevant to a large segment of the population. The idea of representation becomes crucial when you're talking about science. I think it's something that, obviously, as an artist, I'm always struggling with technology. I'm trying to figure out ways in which I can make interesting pictures that are relevant to the time that I live in. But at the same time, I think for scientists, the same thing happens. They have to make their findings visible. They have to give them some kind of visual rhetoric that they can get people involved in what they're doing, can support their findings, and therefore make them practical. I was, for years, I've been, every time I see a scientist, I go bug the science for something. And I think it was about 11 years ago, I was invited to speak at the TED conference in Monterey, California. And if I was talking to somebody who worked with a marine biologist, I would go there and ask everything I wanted to. But then I started talking to somebody that worked at Intel, bugging this engineer about the possibility of making tiny little drawings. And then I said, if you get something that's silica-based and use the robotics that you use to make circuit boards or chips that are very small, can we make pictures with it? And he said, well, why would you make pictures with it? And I said, well, why would you make ships with it? And if you have something that can do something, what can it do another? Just for fun, you know. So people will ask you this, will ask me the same question: why did you do it? You know? So I started there, and he put up a team together, and they started using a fib, which is a focus ion beam, to etch lines on tiny little grains of sand that are virtually invisible to the naked eye. When you look at these things, you don't see anything. It took me, I think sometimes I hate to have ideas because then you have to go out and do them, you know, and it's a lot of work. And this is when you plagued by that, it doesn't work. Then it's even, if it worked the first time, and then it took me 11 years or 10 years to actually be able to do it again, because the team got dissolved. They were in Pasadena. Some people went on to do work on the different ship, and now it's in the Apple computers, and we could not do it a second one. And I was invited to speak at MIT on a multimedia and creative forum by another fellow that you're going to see is Marcelo Coelho. Actually, is the guy who introduced me to Tal. And when I met Marcelo, he said, what would you like to do if you came to MIT and play? Because we have an artist residency here. And I said, God, this is like incredible. You can do anything you want. And he said, yeah. So he introduced me to all the workshops. And imagine for an artist like myself, these guys are so cool. You know, the people from the camera division, for instance, they actually made a camera so fast they can photograph, they can film a photon going through a soda bottle. They can film light. You know, it's insane. You know, I go home after seeing the little video, and I could not sleep for like 2 days just thinking about it. But how can they? Wait a second. They can film in the light that goes the light. I could not, you know. And when they asked me about what I wanted to do, there were two things that I said. Oh, there's this work that I want to do in tiny little grains of sand. I want to make these castles that I drew by hand, and I want to etch them on grains of sand. And they asked me, why would you like to do that? I said, because I want to throw them back on the beach. And then, you know, so people will go to the beach and they know that there's a castle there somewhere. And you say, you know, in this beach, there's a castle, you know, but you don't know it, where it is. I remember that I've been to Salvador in Bahia, and they told me that church that's right in the front of Salvador, you know, the Portuguese, when they built, they brought all the stones from Portugal. And that boat sank right into the bay there, in the harbor. So I said, they always tell me there's a church in the water there. And I keep wondering about the church. So it's like the same thing, you know, there's a castle in any beach. But then obviously, I started talking to Marcelo, and he says, oh, to do this, we can use this machine that's already collecting dust in it, because they weren't using for anything. So we had to fix the machine. We had to actually learn how to use it. We had to write software, because, you know, if you translate a drawing this big to something that it's invisible, you know, and it's actually the drawings that you see here are made by, it's not a tool that etches it, it's actually a stream of particles that's smaller than an atom itself. And then how to picture this, and you use the same machine that etches it is the same machine that actually scans it. And to find a way to do it, it's insane, because you have to scan many, many times to get to that resolution. You don't have a microscopic picture with that resolution anywhere. So to make something that has never been done before, you have to have a lot of resources around you, and also you have to be a little crazy, you know, because there's no reason for this to be. Another thing that these were the sand castles we made so far over a period of 3 years. We managed to make like 8. They're very hard to make. The other thing is, like, when I talked to Marcelo, I thought, oh well, I like to meet with people who work with biology, because I have an idea to do pictures with living things. Maybe, but I was thinking lichen, I was thinking mold, I was thinking like big stuff, you know, and to be able to make time lapses of something that would grow and destroy the picture. But one thing that I haven't used yet was a living material. And then when you in MIT, if you ask for this, you always get a lot more than you ask for because it's crazy. If you say I want to photograph something in a sand, they give you they look at the grains of sand that I was presenting. They say, these are too big. We have to get them tiny. It's so small that you can at that scale you cannot clean around it. So that's why you have all the rocks around it. They're dirty, but they're that's the scale that does it. I can go into detail how they're made, but just to this when Tao gets into the picture, I get introduced to Tao, and then the first thing we were thinking about is actually to print with bacteria. And Tao was like, I said, well, but I can synthesize bacteria. I said, how can you do that? He actually programs the bacteria like you do it with a computer, and then it just produces a different dye, a different color. He'll be much more precise than I am explaining this. But that's just to think that you can create an entire gamma of colors and print with live bacteria. It was fascinating, except that bacteria clogs the needles of the inkjets. So it was a lot of research for nothing. I don't know, but maybe he got something out of it. But we became obsessive in doing something. The fact that also at that scale that we're working, that would allow bacteria to be printed on, you wouldn't be able to see the units. I basically what I've been doing throughout the years is I'm pretty much like a mosaic artist. A mosaic is something that you have a little bit of a tension between the whole and its parts, and you can identify parts that are making the whole. When finally Tal said that we would have to actually make these stamps on a clean room. When you see science fiction films where you have the people all dressed in white and they move very slowly, for drama. And they make so these stamps are really, really small. And I'll let Fortal to explain how they're made. But then the first idea was to make patterns. When you think of from an artist's perspective, okay, I don't want to offend yours, but what an artist thinks of the organic world, the living world, everything sounds very messy. You're talking about little bugs crawling around surfaces, and whenever you put a microscope on something, you see paramecia. They look completely insane. They don't know what they're doing. You look at cells. You cannot grasp the logic of that. So the initial idea is, why not we get all these crazy things and we make something very orderly? And the idea to actually create patterns, they're very regular, they have a sense of order. But then by talking to Tao and learning more about it, I realized that what I was dealing, the material, had an order that far surpassed the order of the patterns that were created by the human mind. In terms of complexity, they all have systems of behavior that are very regular and predictable. They were so predictable they can be transferred to a numeric scheme, and they could be controlled. I was surprised, and then immediately after that, we started doing very dry patterns. They were very geometric. They started becoming a little bit more Victorian, then floral, and all of a sudden, we're doing crowds in sporting events, where we're doing traffic jams, other types of patterns or organizational structures that have a sort of they're homogeneous. They sort of take over the entire surface of the picture, but they also make you think about order and chaos. To think of these things as living things also is quite amazing, because when you're looking at a picture and it looks like the wallpaper that was in your grandma's bedroom, and then you realize that these are they're living liver cells. There are if you look close, you can see all the nuclei. You can see even the ones that are reproducing. And then Tao is telling me, oh, some of them have 2 nuclei, And for an artist to be learning that a single heart, a single cardiac cell beats by itself, things like that, the neurons don't divide. all the cells in the eyes don't divide, and in the cells in the heart don't divide either. What made it, I thought we was going to be a series that we were just going to say, okay, we were going to do pictures with bacteria, or going to do pictures with living cells, and we just have to have one formula. Turn out to be a small nightmare, because for each cell, you have a different type of stamp that you have to make. They would apply to different pattern, and also they have to be scanned differently. Liver cells, for instance, I learned they're lazy. They reproduce in place, they don't move, so they're like photographing little sculptures. Cervical cells are insane. They move a lot, but they're oblong and they're thin. They look very good when you're trying to make thin lines. So we made a mandala out of cervical cells. And cancer cells are even crazier. You know, some of them, they behave very erratically. Well, Stu, I'm going to pass it on to Tal because he can give you further details, but I think just to summarize the idea or the experience of working with somebody who's at the edge of the technology in which you're living, just make you feel like most of the artists that are still around today. When you think about Vermeer, Canaletto, all the greatest artists that we still, they're subject of our veneration, that we're still looking at them, we have to remember that they were always using the latest technology to make the pictures they were making. They were thinking about science, they were thinking about the cosmos, they were thinking about, you know, the world in which they live. And they have become a reference of the world because in their works, they encompass the ways in which the world could be seen or imagined. I think if an artist does something that's important, and if there's a mission, is not to express his opinions, but actually to serve as a very faithful mirror in which further generations and, you know, people in the future will be able to see through something very simple a picture of the world at that time. But it has to be done with the, you know, with the technology that was available at the particular time. Now, working with Tal and working with Marcelo Coelho, which you're going to see a video later on, just it makes me feel that I'm doing art that's pertinent to the time we live in, and I'm very glad we were able to do this. Without further ado, I talk too much, and I'll just shut up now, and Tal will explain a little bit the process of making the colonies. It's too bad that Marcelo is not here, but we can do this in a later date. And now I know that you guys like science and art. We can talk about little details about how the sandcastles are made. But Tal, thank you.
All right, thank
Please, you know, I'll roll. Give it a hand. Thank you.
All right, thank you, Vic, for the wonderful introduction. Can everyone hear me in the back? Awesome. It's very exciting today for me to have the opportunity to talk to you about the science projects I've been working on. So I'll tell you a little bit about my research and who I am. My name is Danino, and I'm a postdoc at MIT, which basically means I'm a scientist, and I work in the lab, mostly developing new technologies for treatment and diagnosis of cancer, and I'll tell you more about that. And then I'll talk about the Colonies project and how we made these images with Vic, and then a little bit more about what that means from a scientist's perspective. So to start off with telling you about my research, what I've been doing is using bacteria as a way to treat cancer. It's kind of probably something you haven't heard of much before, but the basic idea is that bacteria are these small, single-celled organisms that can in some ways compete with cancer cells. Cancer cells are these crazy cells that can grow and divide very quickly, but bacteria can grow much, much faster, and they can evolve much faster. And so there's some ideas of using them as a treatment for cancer. And it turns out that this was discovered by accident over 150 years ago, and it happened when a female patient came into the hospital and she had a tumor on her neck, and they put her on the bed of a previous patient that had a bacterial infection. And this was before anything was known about sterility, and what happened is she got all the symptoms of a bacterial infection, but over the course of about a week or so, her tumor stopped growing. So this was the very first idea that bacteria can be used as a treatment for cancer. And a famous surgeon named William Coley found this case and 47 other cases where people who had bacterial infections actually had their tumors grow slower. And so he started injecting patients with bacteria. He found a lot of them actually had their tumors shrink. Some of them stayed the same size. Some of them didn't respond. But the problem with kind of technology was that the bacterial infections were quite dangerous. Patients got severe fevers and oftentimes were very close to dying. So at that time, in the early 1900s, the beginnings of radiation and chemotherapy, which you hear about a lot today, is the popular way to treat cancer, sort of put this kind of research on to rest. So it didn't really surface until just recently in the last few years when people like me who know how to engineer bacteria to make them do things they don't normally do, make them a little bit safer, make drugs, started getting interested in using bacteria for cancer treatment. And this is a part of a really interesting area of research that we call synthetic biology, which is, I'll talk about this more, but basically we genetically program bacteria to do things they don't normally do, to make medicines, to make fuels. That's something that's very common here in Brazil, or to treat disease. And essentially what we're doing is we're scientists that are manipulating the DNA of bacteria. And to sort of step back a little bit further, as you guys know, DNA is the molecule that's responsible for all of life on the planet. Every organism has DNA. It's sort of a double helix structure that you may have seen in textbooks, and it has letters like A, T, G, C. And the sequence of letters is what dictates who you are. It's what dictates, you know, if you have curly hair, the color of your eyes, the color of your skin, personality traits. And bacteria, along with humans, all have DNA. So bacteria have about 1 million letters of DNA, whereas humans have 3 billion letters of DNA contained in every single cell in your body. So it's crazy to think about this code that's in every single one of your cells that controls a large part of who you are and what you look like. As a scientist, we're basically at the point of technology where we understand what those sequences are, but not so much how they interact together and how to manipulate them to prevent or treat a lot of diseases. But we do know how to do this for bacteria. And so what I'm going to tell you about today is some of my work in manipulating bacteria to do things they don't normally do. Now, what you're looking at here is something that you don't need to understand, but to me is it is a little bit complicated. To me, it represents a blueprint for how you will program these bacteria. We do that by actually making or printing small pieces of DNA, assembling them together, we know what they mean, and then putting them into a bacteria to have it change a certain color and to turn itself on, turn on this color, turn off this color, do things like that that would allow us to study the bacterial behaviors. And so this blueprint that you're looking at here actually allows bacteria to produce this green color and to produce this green color in an on and off fashion. So that was a pretty cool movie. Basically what you're looking at is bacteria that are producing a fluorescent protein. They turn it on and off. Every bacteria turns into 2 bacteria about every 20 minutes or so. So they double very, very rapidly. And what you're looking at is actually a microscopic image of bacteria. So this is actually magnified 1,000 times more than your naked eye can see. And then this microscope takes a picture every 2 or 3 minutes for many, many hours. And then we can compose this movie and play it back in fast forward to see how we've programmed these bacteria. Now, one of the things I did as a graduate student is you see these bacteria, they all turn on individually. Some are on, some are off. And what I did is engineer them a little bit further to communicate with one another. So bacteria out in nature, they're not individual organisms. They talk to each other. And they have different kinds of languages to tell themselves when to invade a particular host or when to become something like a film or resist antibiotics. And so I use this system. I program these bacteria to talk to each other to turn on all at once. And that's what you see in this movie. Yeah, this is a cool, interesting movie.
This is art.
And also, feel free to interrupt me if you have any questions. What you're looking at is this group of bacteria. They're all turning on at once. They're all turning off at once with a period of about an hour. And what's interesting about it is it's kind of like if these bacteria are sort of like us hanging out in this room. You guys can all hear me and we can communicate and maybe stand up at the same time or clap our hands at the same time. But if you think about making this room way, way bigger, 10 or 100 times bigger, you can't talk to the person all the way in the back. And so the same thing happens with bacteria. It takes them a while to send the signal. And so in this next movie I'm going to show you, these bacteria, instead of talking together all at once, produce something like a wave. It's kind of like in a soccer stadium when you all raise your hands. It takes a while for that to propagate around the stadium. And that's the same thing that these bacteria do. Okay, so again, what you're looking at is a microscopic movie completely filled with bacteria. They start talking to each other, but it takes a while to travel down this really long chamber, this really big room. One of the most interesting movies that we generated was actually one where we watched a small cluster of bacteria and how it develops and how it grows. And one of the things about these engineered bacteria is that they only talk to each other when they're loud enough. There needs to be a lot of them in the room before they can produce this color or this signal. And so that's what you're going to see in this movie, is that they only start turning on once they've reached it's called a quorum, and then they start to grow and grow and produce these waves of fluorescence. Okay, so watch this again. It's not blue at the beginning, and then now it sort of explodes. And then it keeps growing and exploding. On the edge of the colony, you don't see any fluorescent colors because there's not enough bacteria there. And for this, oh, go ahead.
I wanted to know when you say they communicate with each other.
Yeah.
Through sound, in fact?
It's actually, they communicate through a small molecule that they make. So they make this little molecule, and it can go through their bodies and into the body of a neighboring bacteria. And then that bacteria can hear it's not actually listening, but it can sense that chemical and then make some more of that chemical to talk back. It's actual, yeah, like sort of diffusion or touch of a small molecule. Yeah.
They can also communicate without contact. So there's mildly telepathic somehow. Yeah.
Yeah, exactly. That's a good point. It's kind of like they sort of like me and you were throwing a ball to each other back and forth. That's the communication scheme. So this is probably one of my favorite movies. It looks sort of like an exploding star, which is why we called it the supernova. And this is an image of the supernova at a gallery, a science art gallery at MIT in the building that I work in. And when I graduated from school in San Diego, one of my friends actually turned this into a cake. So what you're looking at is this supernova cake. It's I think it's like a chocolate beer cake
Yeah, it's a bacteria cake.
Bacteria cake.
The cake was actually like this after 5 days that was left.
Yeah, that's true. So it's funny because you could see the little bacteria on the cake. They're little frosted bacteria, and nobody really wanted to eat it at that point. But I'll show you just a few more movies. I think these are really engaging and interesting. A graduate student that I worked with when I was leaving San Diego took this one step further and now said, okay, if you have bacteria in this room, if you connect these rooms together somehow, uh, almost with a wireless signal, but in scientific terms, allowing them to communicate through like the gas phase or through air, almost like sound, they can communicate farther. And so what he was able to do is make movies that look like this. And so what you're looking at is sort of imagine it as these long hallways that open up into rooms that are completely filled with bacteria. It's like sort of like a dormitory for bacteria. And these bacteria can communicate with one another wirelessly, which allows them to do this over very, very long length scales. And using this sort of technology, we use these bacteria to actually sense different kinds of toxins in the environment. For instance, arsenic is a groundwater contaminant that is very dangerous in developing countries. And these bacteria can sense that molecule and then flash at different frequencies to alert the presence of these kinds of toxins in the environment. And that's sort of one of the interesting applications that I'm interested in. But we also made sort of designs with these bacteria, and we had them spell out the name of the school I went to, UCSD, and have them do this on this very small little device. Actually, the size of what you're looking at is very, very small. It's probably, you know, maybe about like this big if you can see it, like 2 millimeters or so. But it's a living sign completely made up of bacteria that have some really interesting properties. This is, you know, a very fun part of my job to make these movies and study how we engineer these bacteria to do things for us they don't normally do, but also to study how they behave in nature. And I'll just say one more thing on this topic, which relates to my research. And you saw all these things that we can do with bacteria, have them glow, have them communicate with one another. And the technology that I developed at MIT is an engineering of a probiotic bacteria. So you guys probably hear about probiotics. They're in yogurt. They're good for you. There's so many bacteria that are actually good for you. They're not all bad. And I engineered one of these probiotics so that when you orally deliver this probiotic to a mouse, it can actually find tumors in the body, tumors that signify cancer, especially in the liver. And then once they're in these tumors, they can make a small colored molecule, the same ones that you saw in those movies, and change the color of your urine. So the idea is you take this probiotic, and if you have cancer or tumor somewhere, your urine would change color. It would change to sort of like a purplish color. And if you don't, your urine stays the same color, which is a, you know, a very exciting, I think, technology.
This is being very modest about it. Imagine you go to a pharmacy, you buy a probiotic. You know what most of the cases of death, most of the deaths caused by cancer is because of diagnosis, late diagnosis. With this, you could ideally, because he's working on it, anybody could just go to a pharmacy, take a probiotic pill, and if it's like a pregnancy test. If you have a tumor, it comes a color. If it doesn't, it comes another color. And from that on, to be able to program the bacteria that find different types of tumors to produce different types of color is on the way. So imagine you would just popularize and make it affordable and available, early diagnosis to everyone. You know, so it's really cool. So, you know, just to put it like that. Okay.
Yeah, I think that's a good way to explain it. Um, yeah, so this is, a very, very exciting technology. It's very new. It's, I think, an area that I think people should be exploring more. And it's something that, we know right now works in mice, and we're working on the steps to make this sort of more sensitive and more effective and eventually get this to humans. That's a good question. So, yeah, when you build a diagnostic like this, you oftentimes think about how many people that have cancer does it not detect, or how many people who don't have cancer does it say they have cancer? And there's the sort of these false positive, false negative rates. This kind of diagnostic is around the 95% range. So it's very, very good. And that's actually, if you tested a random person out there, it would give you 95%. If you knew ahead of time for that person at an early age what their level was, and then you tested at a later age, then it works even higher percent of the time. So sometimes certain kinds of medical tests require you to have a baseline, and that allows these tests to be more accurate in the long run. Not like a test? Not yet. So I actually don't know how it is here, but I probably similar. But in the U.S., the government regulations for testing engineered probiotic, genetically engineered probiotic, is pretty strict. It means you need to do a full clinical trial before you can start giving this to patients or have it at a pharmacy. Um, which is interesting, because probiotics, you can buy them all everywhere. I mean, they're healthy for you, and yeah, I mean, part of like a frustration for me as a scientist is having a lot of these regulations when there's a very promising kind of technology out there that is at least worth exploring. I can't say that it's the best technology right now, but it's something that's worth exploring further. Okay, so that was a little bit about my research. When I met Vic go ahead.
I just want to make it. When I met Tal, he's going to say about our meeting, and one of the things that when he told me that he was working with bacteria and what he was doing with bacteria, it just occurred to me that he was tapping on a still a very unknown, very unused part of our bodies. That we have an abundance of bacteria in our body that's unbelievable. 10% of your dry weight is pure bacteria. Just picture this: if you weigh 60 kilos, you get 2 kilos of bacteria. Imagine 2 packages of açúcar união of pure bacteria, and if you take like 2 or 3 tablespoons of that, you die because you need that bacteria, and then so you have an amazing amount of untapped, resourceful substance that nobody really cares because if we deal, I think, part of it, if I'm wrong, we always think of bacteria as something that is outside. We have still a sense of self that's very strange, and it's not very inclusive, and it segregates bacteria to different levels of value that sometimes keep us from using them. When this guy told me I'm using bacteria to diagnose cancer, I'm using bacteria maybe to cure cancer, I said, why people haven't used bacteria for anything before? And it was really amazing. Okay, go ahead.
It's very true that I think that bacteria are everywhere in our bodies. They're in our guts, but they're on our skin, they're in our mouths, and people right now are just discovering what kinds of bacteria are in all these places and at different times of our lives that change the way that certain diseases progress. And so it kind of represents a very natural platform for developing modifications to our bodies by changing the bacteria. Instead of, changing our cells, that's kind of something I think that is a little bit crazier to think about. So when Vic was at MIT and I showed him all of these movies, we basically started thinking about ways that we can make art out of bacteria or out of cancer cells. And one of the first projects that you see here is actually a petri dish of bacteria, and it's on the top left. And it's a picture of Vic, if you guys recognize it. And that picture of Vic is actually made up of his own bacteria. So when he came into the lab, I took a swab of his mouth and I grew the bacteria that were in his mouth. And then we painted this onto like a petri dish that was about that size. That was the very, very sort of genesis of this project. As Vic talked about, we found all these bacteria that can make different colors, a wide variety of colors, green, blue, fluorescent colors, colors that are, dyes in clothing. Bacteria can make those things. And they can make all kinds of interesting designs that we can basically paint with them and develop this sort of palette of bacterial colors. But I think, one of the things that we were a little bit unsatisfied with is, as Vic said, sometimes you want a connection between the individual objects and the image as a whole. And in these sort of petri dish drawings, you don't really see the bacteria. If I didn't tell you they were bacteria, you wouldn't know that. It kind of looks like a paint or like a glue. And so we wanted to be able to see both of these things at once. And what that meant for me is I had to think about making very, very small images and using a very high-powered microscope to see the individual bacteria and the image as a whole, sort of like these paintings that you see here. So to make that, the video that we're going to show is going to talk about this a little more detail, so I'll explain it in a very general way. It's basically, think about making a stamp, like a rubber stamp that you use, and you stamp it in a dye, and then you stamp it on a paper and you have the design. Except now this color dye is actually something that cells or bacteria can stick to. So after you make the stamp and the cells stick to it, you can shake off all the other cells, and then you can take a picture of these cells on the microscope. That's basically how we make these images. And it turns out that it was a lot harder than that. And sort of one of the things that Vic mentioned is that every cell had sort of a different kind of sticky material. We had to play around with what cells look good in certain images. And actually, a lot of the features of these designs are on the same size as a cell, which made it very, very difficult to make these stamps. We had to go into a clean room because a piece of dust can get onto your image, and would ruin the image. A piece of dust is quite large. It's probably the size of one of those flowers that you see over there. So that was sort of a little bit of the challenge in making these images. But we ended up with really interesting patterns that Vic chose. To me, this one sort of looks like a wallpaper, and it's made up of liver cells, healthy liver cells that we get from our rat because we're interested in studying how the liver functions. And the closer that you get to this image, you start to realize that it's actually made up of something else. It's made up of cells. And these are what we call hepatocytes or liver cells. Each of them, I don't know, I think of them as having their own personality. They have like their own shape, their own nuclei, which is the nucleus, which is the yellow dot that you see. Every cell has a nucleus, sometimes two. And that's where all of our 3 billion letters of DNA is contained in that small little dot that helps these liver cells function. So that's sort of what I mean when we have these sort of two scales, one where you can see the individual object and one when you can see the object as a whole. And this sort of, I think Vic will maybe talk about this more, but has sort of an artistic purpose in some ways. After we did the liver cell paintings, we did this with a lot of other kinds of material, bacteria, E. coli, salmonella, stem cells, cancer cells, liver cancer, colon cancer, all these kinds of cancer cells. And basically we built all these kinds of materials that we can paint with and develop pairings with images to tell interesting stories about these kinds of materials. So I think to me the most interesting story is the images that are made up of cancer cells. And as a scientist, I think cancer, it's kind of, you have this interesting relationship with working on cancer. In the everyday world, like if I'm just talking to you about cancer, it's a very negative word. It's something that is very personal. It draws a very emotional connection because we've all known someone who has or had cancer, and there is like a very strong stigma associated with cancer. You automatically think of death, and then for me as a scientist in the lab, I work with bacteria and I work on developing these treatments for cancer. All those movies that I showed you about, they're very light and they're very exciting to me as a scientist to come into the lab and work on these kinds of technologies for cancer. And at the same time, if you watch these movies of cancer cells, they're really fascinating. These are cancer cells that are moving around in a dish. They crawl around. They're searching for food. They double every 24 hours or so. This to me is something that's very exciting to study because we can learn a lot about how cancer cells behave and sort of develop like new treatments for cancer. So these are cervical cancer cells. They're called HeLa cells. And this is an interesting story by itself, but they're called HeLa because they come from a patient named Henrietta Lacks, who was they come from the same person, yeah. And it's a lady who was around in the 1950s who had a very, very aggressive form of cancer. And this was the very first time we even realized how to grow cancer cells in the lab because it's very hard to grow cells. And her particular cells are just now spread everywhere.
So every single cell that you do research comes from this woman. So that's why they called HeLa. Is the short for her name. So she lives on in every single lab in the world where the people do cervical yeah.
Oh yeah. So this is one of those stamps. That the cancer cells.
This is an enlargement of one work, but you see how they're very nomadic. They move around, and that makes the scanning process very hard sometimes. So for each type of cell, we had to devise a different type of imaging. It's not just like a series that you get, find out a way of doing something, you just apply to it. So each piece from these series have a completely different process about it. It has to do not only the way you put the cells there, but also the way you picture them.
Yeah, definitely. So those are, the things that I think about when I'm making these images. On the one side, cancer is this very bad thing, and on the one side, there's an excitement. And for me, those kinds of relationships, became intertwined maybe a year or two ago when my sister was diagnosed with cancer. And so it became sort of a very personal thing when you know someone that's close to you that had cancer, and you work on it every day. It put a lot more meaning to the kind of work that I was doing, and sort of intertwined a lot of the reasons of why I have been studying cancer for a while. I think that as part of going through something like that, people say the best thing to do is to create something new, to create something that's beautiful, like one of these images, something that you can share with everyone to experience and talk about cancer. So I think it tells sort of a personal story for me, but it also tells a story about my research. This is an image made up of bacteria. And I think when you look at these images that are made up of cancer or bacteria, you start to wonder what these things are and how we're using different kinds of technologies to develop treatments for cancer. It makes you think about what are the things that we're not researching that maybe we should be researching more. And on top of just raising awareness, it also helps raise money. Vic and I are planning to donate some of these proceeds to cancer research, to specific areas that are not well studied. And I think these kinds of artist and scientist collaborations are something where artists can help develop methods to communicate the science. And as you guys saw, a lot of the techniques that we developed to make these images are very brand new. Scientists have not even learned about these techniques yet. They're quite challenging. And so we, in fact, develop very new science by being challenged by artists like Vic. So I'll end by just sharing that, cancer research and probably everything is a collaboration with a lot of people. My advisor, Sangeeta Bhatia, is a really amazing person. She's very creative and open-minded, and she lets me work on a lot of interesting science ideas, but also collaborations with people like Vic. There's a really talented group of students that are involved both at MIT and at UC San Diego, along with my advisor, Jeff Hasty. And also thank everyone in those labs and thank Vic for all the support. And working with him has been really just a pleasure because he's so interested in science, and I'm also interested in the visual communication of science. And so somewhere we have a lot of overlap together in developing these sort of interesting directions. And it's been a really great time working with everyone in his studio as well. And then I also want to thank Mariana for inviting me here today, and for everyone for coming to this lecture and listening. All right, thank you.
You know what Tal just said is quite interesting because when you talk about bacteria or cancer, or even when you talk about liver cells, healthy liver cells, you're talking about parts of our existence. When I say our, I said as a group, of our society, that because we cannot relate to them directly, we need like machines, instruments, everything that you subject to a scale change, a radical scale change, becomes something of the mind. It's not something that you can relate physically. It's not ergonomical. It's not like this glass that I know its size, and I feel very comfortable with this glass. But when you think about a virus, you think about a bacteria, these are things that you can only make assumptions about them. But unfortunately, not all of us they have access to a very educated, a very thorough knowledge or information about what these things really are. As Tal said, once you start messing with these things, playing with them on a microscope, you become familiar with them, and they become part of what you do. They become natural, For most people, when you talk about virus, bacteria, cells, your innards, like things that are inside of you, immediately there is a repulsive attitude to it. I remember a few years ago when I was doing something with garbage. Garbage is also something that is part of our history that we don't want to have in our family albums. There are things that you want to move away because they have a connotation with death, with something that it's not you anymore. A lot of these taboos, a lot of the negativity that revolves around these issues, such as garbage or virus or bacteria, have to do with sort of a denial that we may live without dealing with these things, that we may live without dealing with garbage as well. And that, I think, is where the problem begins. We are denying knowledge, we're denying contact. So something that's very important. So issues that are very, they're really seminal to our existence. When I was doing things with garbage, one thing that was attractive to me is to make the most beautiful picture out of something that you don't want to look at. And immediately it creates a dichotomy, a paradigm that when you're looking at this, you really want to look at this. Perhaps for the first time of your life, you're looking at garbage with a different kind of a perception, with the fresh eyes, or actually you're just plainly looking at it. Perhaps by creating this little gimmick that makes you see beauty, it gives you the feeling or the comfort of logic, symmetry, constance, security, that a pattern sort of is able to pass on to you, and allows you to, from your fears, from your ignorance, from our ignorance, to look at a cancer cell and look at it for what it is, something that is part of our lives, part of our existence, something that we have to deal with. I think it's like kind of I talk a lot about realism, it's to be able to connect to these things. It's really important. I mean, there's a painting by Géricault that is, well, the most famous one is the Raft of the Medusa that's at the Louvre, and that portrays a catastrophe, people who are dying, dead people. That's never, that's also part of the subjectivity that's been artists try to avoid, because it's not something that people want to hang on the living room, a scene of death. But it was real. It was something that was a fact that existed, and it was part of the drama of the time in which this painter was actually producing work. And I think that to be able to actually create this connection with these invisible realms, that they're not only invisible because they are too small or too large, but they're invisible because we don't want to see them. They say that the worst blind is the one that doesn't want to see. I think it's really important, and it could not be done without this partnership. I don't think in one way, I sincerely hope that people will look at things that they don't want to look at because they don't know more, but it will be so beautiful, it's so attractive, that they're going to look at it and they're going to say, wait a minute, let me know a little bit more about this. They would break a little bit of the taboos, a little bit of the resistance that we have to deal with things that we don't want to deal with visually, because it's just a matter of presentation, is how they come to us. And these are beautiful, beautiful, virus-infected cells, if there is such thing. I have a lot of, I think when you talk about aesthetics, a lot of what happens with aesthetics is familiarity. I have a friend who's a surgeon, and one day we were having a drink, and then he came. He said, "I'm sorry, I'm late because I had to stay because I had to discuss this with my friends. I just witnessed the most beautiful surgery, open heart surgery that I've ever seen in my life." And I said, "Beautiful." Yeah, it was amazingly beautiful, because it has the right narrative. Everything was like a Tai Chi, And I said, "But aesthetically beautiful." And he thought about it for a while, and he said, "Yeah, it was a beautiful open heart surgery." If you can imagine that. And I keep thinking, it's like the same example that I got to the black hole collision, like this is something that cannot leave my mind. I've been trying to picture in my mind this beautiful open heart surgery. I can't, but it's an obsession. And maybe the new series will be open heart surgery, beautiful ones. But and I'll have to, if there's any heart surgeon here, I'd like to collaborate with her. But we have these two presentations that were videos that were made for the Creators Project, which was the first one I did on the sandcastles, and it was an amazingly successful because we're talking about bacteria. Something that's fascinating about bacteria. That until very recently, the whole idea of knowledge was something that you could hold on to. Knowledge and property, culture and property were very associated. You know, and when you start looking at bacteria, you realize that we are kind of bacterial, because in our time, we're start to realize that knowledge is what we can send out, that we can transmit, that can, in this way, that can outlive us. This is what bacteria does so well, and so much better than we can do it. You know, they just transmit everything by RNA, just touch each other. You know everything that I know. I wish it was like this. Not for everybody, of course, but you know, but it would be quite wonderful. But I think the first one, I think we're gonna just go through this video that was made formatted for internet, and then we're gonna go to a second one. This is not out yet, so it's a world premiere of the Creators Project video. It's not available on the internet yet. It will be soon, and then we're gonna see the other one, and then we'll open for questions. I always love to collaborate with scientists because it gives me an idea that we can perhaps meet in the middle somewhere and make this perfect piece of art. It's exactly this combination of matter and meaning. Not only is a collaboration between a scientist and an artist trying to make pictures out of living things. Tiny, tiny living things.
There's prints of bacteria, cancer cells, and also cells that have been infected with viruses. And the series as a whole is basically pairings of these materials with different types of images that tell a story. I got interested in art as a graduate student when I was making all these bacterial movies, and I found them to be a lot more convincing when they were both beautiful and interesting science. They have a rhythmic behavior. It's almost musical, or you can imagine these bacteria sort of like dancing at a rave or something. I met Vic through a friend at MIT, and then I started showing him all of my bacterial movies. And he was like, yeah, we have to work together. And I remember the next day he came to the lab.
And he said, what about, can you do like a picture with like my bacteria? He immediately got this swab and said, open your mouth. And I said, now? And he said, yeah. So he stuck this thing in my mouth.
We made a self-portrait of Vic with the bacteria from his cheek. So that was the very beginning of the project.
I never would expect that I would meet somebody that was working with that level of complexity. To my surprise, he could do it, and to his surprise, it was a lot harder than he thought it was.
In synthetic biology, we reprogram life, and we start thinking about the ways that nature designs life and the ways that we can imagine redesigning life to do things that they don't normally do. Here at MIT, what I've been doing is actually engineering bacteria to detect cancer. And the idea behind that is bacteria can actually grow within tumors. Once they grow in these tumor environments, you can get them to sense that environment and produce a molecule that allows you to easily detect the presence of a tumor.
We think of bacteria as something bad, you know, but in fact, they rule the world. We have more bacteria than human cells in our bodies. If we didn't have a small portion of these, we would be dead. It's a lifelong collaboration. To think that we could use that also, that is so present in our lives, inside ourselves, to create an image, to make you look at them for what they are, you know. They're fascinating things. We started with very simple patterns that would pair something that is, in our minds, very chaotic to something that's very orderly, something that was created by the minds of men. But as soon as we started doing that, you know, we felt tempted to try different patterns, like traffic jams, crowds in sports events, circuit boards. It's like somehow trying to pair mind and matter together and see what comes out of it.
The process for making these images consists of 3 steps. The first step is to make a master image wafer using photolithography techniques. The second step is actually to cast a rubber stamp from this wafer and use that stamp to make a sticky image on a dish that cancer cells or bacteria could stick to. And then the final step is to apply cancer cells or bacteria to this dish and allow them to bind to the sticky material and take images on the microscope. You can actually see the individual bacteria in cancer cells with this high-powered microscope. But then if you zoom out, you can actually see the image in its entirety.
It is quite beautiful to actually have a picture of cancer cells. Something so scary, you know, and something so outwardly, and transform that into something that could inspire beauty.
Cancer is a very complex word. It's something that has a very strong emotional connection. And in the everyday world, it's one of the worst words that you can imagine. You automatically think of death. And then for me, as a scientist, you grow these cancer cells in the lab. You want your cancer cells to be happy and healthy for your experiments to work out. And in fact, one of the worst things in the lab is when your cancer cells are contaminated and they die. It's a very different kind of relationship with cancer that we have. And I found that it was really interesting that in the Colony series, we can sort of explore this beauty of the cancer cell art that we're making.
For these things to become part of everybody's life, you do need a picture. You need a way to experience, you know. That's a way in which artists can partner with scientists. They can provide the vision. I'm watching it for the first time. I liked it too. Can we turn off the light? Yeah. Oh yeah. Yeah. Yeah, 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 yeah. But the Bill Viola one, I thought it right away too. It's a Bill Viola, tiny Bill Viola. Got it? Oh yeah. Oh yeah. I didn't see this. Oh yeah, yeah, yeah. Okay. Yeah, yeah, yeah. But I didn't think of that. Yeah. All right. Our relationship to images has an ergonomic relationship. We walk towards images, and whatever is there has a certain scale that conforms to the scale of our body and our distance to it. And as we approach it, something happens. We either find the connection or we lose it. Photography gives you the ability to play with that scale. Once you go beyond and you really blow the scale altogether, beyond the boundaries of what we understand ergonomically. This is the kind of images that I'm always interested in. To think that there is a grain of sand with a castle in it. You know, it's not just a trick, it's real. I used to work in a very small studio, and my work had a certain scale. And then I realized that by moving into a larger studio, the work sort of expanded. In the beginning of I think it was around 2001, 2002, I had the opportunity to work in an environmental scale. We made almost 25 drawings, some of them up to a scale of 500 meters long, and they could only be seen from helicopters. The drawing itself becomes something from your mind. Around that same time, it made me think of going the opposite way around and actually making things so small that would create similar impression. They would be so tiny that it could only be imagined. It cannot be seen. And it was a very fortunate event that I ran into Marcelo Coelho.
The first time that Vic talked to me about this project, I thought he was joking. He came to me, he was like, I've had this idea for a long time and I've really been wanting to do this. I want to draw a castle onto a grain of sand. And I think the sheer impossibility of it is what excited me. And then from then on, it was basically me trying to figure out how to do it. And that lasted about 4 years. The project starts at pre-photography. We started using a camera lucida, which is a drawing instrument that Vic used to draw these castles.
The camera lucida is a 19th century device that allows you to make pictures. It's something that allows you to see what's in front of you projected in a board right below it, and all you have to do is to trace it. The inventor of photography, Henry Fox Talbot, was a terrible camera lucida draftsman. That's probably the reason why he invented photography.
So we start before cameras exist, and we end up at a point where cameras are kind of irrelevant, or they're not even necessary. The machine we ultimately use is called a FIB, for focus ion beam. It's normally used in the electronic industry for fixing integrated circuits. So instead of using it to draw chips, we're drawing castles with it.
This is about 1/2 millimeter, and I'm trying to find a grain that looks good. All right, so I just loaded the image of the castle here, and I'm going to frame it now. On this screen here, we have the ions that we use to etch the grain, and on this screen, we have the electrons that we use to see the grain, and the combination of both is what creates the image. Now just wait 2 minutes. Fingers crossed.
It's really strange because you're basically drawing onto a canvas that you don't quite know what it is, and you can't hold it. Sometimes I would draw and the grain would just break into pieces because it's too soft, or sometimes I would draw and nothing would show up because it might be too hard, and you have to restart the entire process. I don't think I've ever worked on something that was this complicated and difficult. Over the course of 4 years, sometimes I ask myself, should I just do this in Photoshop? But you realize that it's not the same thing. In some ways, the final image carries with it the history of the process that you've developed.
Recognition has been the basic principle of my work since the very beginning. The word recognition is very interesting because it means assimilating something twice. I rely on imagery that's very simple. things that you've seen a million times, because that's what creates this little trick. You think you know it, and then you have to know it again. The idea is that you create a path, but you leave breadcrumbs for the viewer to follow. And this questioning about the image, when you're looking at something, you realize, how the hell was this done?
All right, it looks like we got something here. So this is the first castle that we got with this new batch of grains. It's actually really nice now to sort of navigate through the image and see some of the details. When you look at the castle in the drawing, you see the outlines of the rocks that they're on top of. They're on top of mountains, basically. And they actually match the actual outline of the grain. So there's this really interesting symmetry, right, where the mountain actually looks like the grain of sand, and they're entirely different scales.
The interesting thing about projects that connect scientists and artists, I think, it comes down to the point that we feel that we're always looking for the same thing. You know, we're trying to understand the world around us.
I think photography in some ways is just sort of restarting. I mean, I think there's a whole new kind of photography kind of emerging now. A lot of it is happening because of this combination between computers and cameras. And a new form of storytelling and narrative can sort of emerge from it.
It is a great moment to be a photographer today, because photography is completely obsolete in terms of its relation to reality. We're pretty much at the spot where painting was around 1839, when photography was invented. Painting was sort of released from its relation to the factual world. Painters had to think, what is painting? In a similar fashion, the relationship between photography and reality has changed significantly with the advent of digital imaging. It's becoming what Leonardo mentioned as cosa mentale. It's something from the mind, which has always been.
When somebody tells you, hey, this is a grain of sand, there's this moment where the reality that you have in front of you sort of falls apart, and you have to reconstruct it. You have to really take a step back and rethink what that image is and what it means. And I think that's the motivating force behind Vic's work and why he wanted to do this project.
It's so insignificant and yet so monumental. I'm very happy with the result. We should have started with that. I think we should open for questions now if you have some. If you don't have any questions, I'm gonna pick you. Okay, sorry, no. Maybe you should get a microphone. So.
I think it's incredible that you are reminding us of the obsolescence of photography today in relationship to the obsolescence of painting when photography was invented. I think that's a very.
Well, I think wait. I think it's just gonna have to turn it on. Wait. Okay. No, you could say it in English.
Okay. No, I mean, I think that one very important factor that you mentioned in the last movie is the obsolescence of photography as it relates to reality today, because the manipulation of photography goes so much beyond reality, and the relationship between the invention of photography to make painting as a historical record obsolete.
But
That's amazing.
It's something that may be pertinent to the discussion of art and science. Science deals with things that are. And the scientist is very interested in how they behave, what they are, what they're made of, where they are, when they happen. This kind of knowledge is natural, you know, because every single species that are around today, they possess knowledge of a certain kind. They know something. Otherwise, they wouldn't be around, you know. Every species know, but there's only one species that believe. Believing is something particular to our species. It's something that makes us relate to things that are not there, not around us, or they're happening far beyond the reaches of our, beyond our senses. We believe. But there's got to be something between knowing and believing that makes us like that is what knowledge really is, you know. There's so many, our knowledge is very biased. Until the first pictures were made probably around 35,000 years ago. But in Paleolithic painting, it's a loose record because you can only make certain assumptions. But from the first time somebody made a picture and somebody could see something in that picture, that triggered a race. When you make a picture that looked like an animal, people looked at that and they actually did see an animal in that picture. But a month later, another tribesman, another member of the tribe will go there and say, yeah, that looks just like a little drawing. And the artist had to go there and put some color in it, put some shade on the bottom. And then so on, that we've managed to evolve the idea of representation to what we have today. It's interesting that the whole history of representation describes a constant race between technology and cynicism. It's whenever people start seeing too much of a picture in what you're trying to represent, it was time to move on to something else. In 1992, around the early 90s, or the late 80s, we developed very powerful techniques that allowed us to cross the threshold of discernment, of visual discernment, of what was real, what was not in a picture. Corel and Photoshop techniques, we don't really realize what they will be doing to our concept of history. But it's something that I'm sure in the future will be discussed as something very ominous, very relevant. Because we've gone from 35,000 years learning how to make perfect pictures until the point that the pictures sort of take over. And we realize that we've learned how to lie better than we learn how to tell the truth. Now we can make a convincing version of anything we want, That's so credible that now recently photography hasn't even been accepted as evidence for legal trials anymore. I mean, one thing is interesting about it's that when photography was invented, it was big announcement in France in 1839. The next day, all the news were that painting was dead. And fortunately, you can go out here and go to the shopping mall and buy oil paint today. Photography didn't kill painting. Photography changed the way we relate to painting and freed painting from its relationship to the factual, to the material world. Now it feels like the ghost of painting came back to haunt photography in the guise of digital imaging. And then you have photography is not credible anymore, because digital imaging actually freed photography from its relation to the real world. And then it allowed, the same way the photography allowed painting to explore the medium itself. The painters at the time, they were thinking, okay, so what is painting? That's the seminal question. What is this? They never asked that before because they didn't have to. If you look at a picture of a battle, they not only believe that the battle was just like happened exactly like it was depicted in the oil painting, but they would say, that's a battle. That's not a painting of a battle. What's important now is that we are able to look at photography through its filters. We look at this as process, and we'll be able to understand how this medium or the particulars of this medium have been affected the way we see the world up to now. One thing is that, it's very important to try to find out how things around us function, but also is actually the means to describe this occupation, this trait, also have to be updated continuously. Our visual rituals have to be continuously updated, so so we can keep up with the findings of scientists or the findings of people who are working directly into the world of phenomenon. As I said, that I very lazily separated these two things, mind and matter, as ways to describe the relationship between art and science. I'm not saying that we're both looking pretty much for the same things, using the same ways. Both scientists and artists use a very empirical way to go about things. They're extremely creative occupations, and I find it that we're both trying to polish this very thin membrane that separates mind from matter from each side, trying to make it more thin, more transparent. And it's a very interesting thing. But it's important, when you talk about the idea that photography has become obsolete, it hasn't really. I think I said that into that context, but it has become actually more useful, in a more philosophical way. It's just the use of photography has changed dramatically. Any more questions?
Can I ask Tal something?
No, you already asked one.
Him.
Okay.
Tal, I found it fascinating. It's the first time ever I can imagine bacteria as being sentient, as being, like with minds and with means of communication. I mean, can you talk a little more about how they actually really communicate with each other?
Yeah. It is. That's an interesting question. It's sort of related to what Vic was saying, in that as humans, we sort of can believe we can understand things that aren't there, but bacteria have sort of more present reality, and it's a much more biochemical, obviously, a much more obvious biochemical relationship, in that the presence of certain molecules, when they interact together, turn on other molecules. So they can sense, temperature, they can sense their environment. One of the fascinating things that bacteria do is, if they see food over there, they can sense, kind of like smell, they can sense it, the molecule, and swim towards it. And to do that is an intelligent behavior. And people are starting to figure out how that works now. So it's more complicated. If the bacteria sees some over there and some over there, it has to quickly make a decision as to where there's more food. And it knows how to do that. It can figure out computations between different inputs. And so when you think about that and extending it further, bacteria and cells are sort of like little computers. They're, in some sense, programs that sense the environment, take in inputs, and have to generate a specific output. Maybe that output is to swim, maybe that output is to do something else. But they're very much logical beings. And I guess even like one step further is, they don't just sense the present reality, but they have memory in a way. So encoded in the ways that these molecules are sensed, it can actually affect their DNA, or can affect the computers in which they can store these kinds of informations and go back to it at a later time.
Thank you. When you say you can actually program bacteria, could you elaborate on this?
Yeah. So what I mean by program is genetically program, which means the language of DNA, this sequence of letters, is like a computer code, and every sort of chunk of letters has a meaning. So one chunk might mean your hair is a certain kind of texture. If you change a little bit about that, it might mean your hair is just a slightly different kind of texture. So there is a code to how our genes behave. And so by program, what I mean is to just modify the letters of the DNA. And I think you guys probably all have heard about genetically engineered foods, genetically engineered crops, those kinds of things where for 30 years we've added a gene, maybe one gene, taken out one gene to make a different kind of behavior. In Brazil, there's actually a lot of that going on. But now we're at this point where we want to go past that. We want to not just add one gene, but add a lot of genes. And you need many, many genes to, for instance, turn something on and turn something off. Or if you think about the way that we respond to sunlight and the rhythms of our daily basis, those kinds of circadian rhythms are a response of a network of genes, like dozens of genes that we have in every cell in our body that respond to light. And so my job is to learn about those networks and then build them in a synthetic version in bacteria or in a human cell to add to the kinds of behaviors that they would normally do.
Now and then we hear some cases of shrinking tumors, like someone had a tumor and it shrunk. Could it be related? Is it related to bacterial infections somehow? Does it, as you said, that the lady that was in the bed got an infection?
Yeah, it could be. You know, that historical observation is not clear what the effect was, because by injecting bacteria, you provoke your immune system. Your immune system becomes more active, and by doing that, your immune system can be more active in finding tumors or finding cancer cells. And so there's this very promising area of cancer research now, which is either stimulating the immune system or genetically modifying your immune cells to attack cancer cells, to find cancer cells. And it's very closely related to what I want to do. I want to program bacteria, I want to program viruses, I want to program cells that can find disease and take care of it on its own. And so, you know, that figuring out the code to do that, learning how nature does it, and testing that in experiments and on animals is sort of what I've been doing with my research.
So you say a cure for cancer is possible?
Yeah, this is an interesting question because, you know, scientists don't like to use the word cure. It's like it's a very hard promise to make. People have been using that for 100 or more years about a cure for cancer. Even when chemotherapy was invented, people thought they had found a cure for a lot of cancers. But I will say that in today's world, there's many cancers that are not big factors anymore. A lot of a lot of cancers, even when you catch them in the later stages, have very high cure. I don't want to say cure rates, but they say 5-year survival rates, which is very good. And my sister, who had like a stage 4 cancer, as late as possible, and she had a lymphoma. And lymphomas are some of the cancers that are very well treated by chemotherapies. And so after 6 months of chemotherapies, she's been in remission now for about a year. And lymphoma, even at the latest stage, is around a 50-50 chance for curing it, or at least 5-year survival. So, I think right now we're just improving and going beyond that. And we've reached the boundary in our history for treating cancer with chemotherapy and treating cancer with radiation. And now we're trying to develop new techniques to treat cancer in other ways.
I'm curious about the, you talked about this kind of Wi-Fi communication
Yeah.
between the bacteria, and Vic was commenting about how much bacteria we have in our bodies, some packs of açúcar união. Is there any research on or any knowledge on if this bacteria communicate between bodies of different people, for instance, and
Like, yeah, Wi-Fi, bacteria Wi-Fi. I don't think there is that directly, but
This would be a nice thing, you know, that somebody like trying to get close to you and they say, really, I really love you, but it's my bacteria that really can't stand you, you know, your bacteria. Have your bacteria talk to my bacteria.
That's very funny. I think, you know, but it's kind of an interesting, really, I think one of the most fascinating areas of research is how the bacteria in our body function and cause disease or cause their own health. And you know, it's different from cancer in that cancer is not contagious, you know, but bacteria in your body, we all share in some ways bacteria. We go to the same places, we go on the subway, we interact with each other, we shake hands. These are exchanges of bacteria that we trade with each other. So it's very much an environmental kind of community. As well as the way that your genetics and your immune system tolerates the kinds of bacteria that we share. And those are some of the most like interesting areas of science now, is trying to figure out what are these bacteria doing in our bodies. Do they help us? Do they hurt us? And there's cases of both of those things.
Well, first of all, I would like to thank you guys because you brought so many good news for us here this morning, like from art and science. It's amazing. I mean, those are all good news. And my question is, we are talking about cure all the time or remission, but what about prevention? I think this takes to a huge journey into prevention in cancer, because as earlier as you can diagnose or detect some of the tumors, this is the right way to get them, you know, controlled.
Yeah.
Besides all the complexities that you talk about, something which is simpler, but it sounds to me like, are you thinking about any of the campaigns putting together in terms of prevention, in terms of awarenesses, or what about?
Well, not yet. We haven't.
But what about?
We had a lot on our plate.
What about
Actually,
starting?
you know, it's funny. You don't have the. Well, it's a little bit. We haven't really thought about, but we're trying to come up with ways in which the sales of the artworks can be reverted into funding.
Yeah, because you touch a very interesting point that becoming.
But prevention is something that, no, we haven't talked about that yet.
When you talk about prevention, you go straight against the stigma, which is.
That's true.
Yeah.
And you have to go to China. That's where preventive medicine is always a priority.
You know what we're doing also that we didn't have visuals here? This very fancy company that makes porcelain in France, in Limoges, Bernardo. They asked me to make a set of plates.
Yeah.
And then I went, so Tal was making these really gorgeous Petri dishes, you know, but with nasty stuff like salmonella. So we're making plates that they look like glazes.
Yeah.
They're beautiful abstractions. Some of them are fractals, you know, like they're really, really gorgeous. But then when you see you eat on top of that, and then on the bottom of the plate you realize it's written what it is. It's some really deadly type of salmonella. And you ate right on top of it, right? But it's a picture
that's more
of it.
complicated.
So it just kind of, it just made me think of that. Mariana. All right, guys. I have to catch a plane. I could stay here the whole day. But thank you very much for coming.
All right, thank you.